me start recording. Good morning, everybody, and welcome to Physical Science 110. Today is October 4th. We are starting week 8, and we have a brand new topic, basically, that we're going to start. So before further ado, let me show you what I'm talking about. Okay, I'm going to switch cameras. First of all, let me pull this one up a little and change cameras. Okay, and let me remove the background because the background is on the way right now. Choose background, none. Okay, so basically what I have in here, I have a piece of paper, okay, and I have a rod in here. This is basically a glass. I'm going to rub it through a surface and then bring it next to the paper. It picks it up as opposed to the force of gravity, okay? It's not strong enough right now because probably it lost some of the, gets entangled with the for some reason, it's not lifting off of the surface. Let me try it again. Okay, there is some interactions. The point being in here is this force is an electrostatic force, and you've experienced it in your life. So you really don't need a demo from me to see it at work. And let me try it one more time to see if I can get a different surface. Maybe it's going to work better. Sometimes the tissue, or maybe if I can change the tissue in here. Let me grab another portion from this tissue in here. Okay, and let me rub the rod again one more time. If it fails, okay, it worked. As you can clearly see, this force, which is the electrostatic force, is much, much stronger than the force of gravity. The force of gravity is the force that is responsible for any object, like this piece of paper, the one that I had in my hand, basically to fall to the ground, okay? So the reason why it's sitting in there to begin with is the force of gravity. The force of gravity is the one that causes it to exist in there. Obviously, in trying to understand what's going on, we came up with the electrostatic force, the force that is responsible for electricity and magnetism. This is basically a circuit in here that takes advantage of that, okay? So this is the typical circuit. This is transformer. These are capacitors, okay? And you have in here resistors. These three things are resistors. And actually you have here transistor in here, the connection that does all the things. And you are careful enough, you might even find circuits that have inductors in them and things like that. Usually near the power supply, there is inductors, like this transformer. Anyway, so let me get into the objectives of the week, and let me, probably I can keep that on focus, it's fine. Okay, or let me change cameras again. We're gonna come back to this demo and more demos to understand what's going on in here, okay? So let me put back the background because I don't want to see the ugly background in here that I have, and let me change the camera. Okay. Close that window, and let me share the screen so that we're on the same page on where we stand. So again, we are in week 8. And today's topic, as you can clearly see from the demo, has to do with electricity and magnetism, okay? And it's really the electrostatic force, to be more specific. And you have this page for you guys as an intro. Don't forget that you have a quiz this week, okay? You'll be quizzed on the content that you've learned from last week, okay? So actually, let me go back home so that we see exactly how we got in here. Yes, Sabine.
I went on Canvas and it tells me that there's 2 quizzes we have to do.
Okay. This week is quiz 7 from week 7, and probably it's still yeah, the other one is due October 9th still. Both of them are due on the same day. Okay, one from week 6 and one from week 7. Okay. So this is from the week before last week, and this is from the week of last week. And this is the new content for today. Okay. So let's get going with this. That answers your question, Sabine?
Yeah, thank you.
Okay, very good. So basically, in trying to understand what's going on with this branch of science, basically, remember we learned F equals to ma. This is Newton's laws of motion. Basically, 3 of them, but the biggest one, the biggest deal actually, is the second law. We know that there is a force between this rod. Where did I put the rod? And this rod, when I was doing the demo, and a piece of paper, for example, when I rubbed it, okay? So there is a force in here that would cause it to stick to one another. So this is an attractive force. In some other demos, what we can do, actually, we can do a reverse force, in which case, basically, the two, they will repel instead of attract. For that, we can use actually a tape. I don't have any here, tape with the glue on one end, and you can basically make another replica of it, and you bring them one another, they will repel, okay? So similar charges repel that are made of the same stuff. You make them with the same conditions, and opposite charges attract, okay? That's one thing. Furthermore, this interaction, this force depends on distance between the two charges. If the distance is close, the force is strong. That's why I had to bring the rod closer and closer from the other one, from the paper, for it to interact. Okay. So the distance matters, and it's an inverse square law, and it's also proportional to the charges themselves. Obviously, if you don't have a charge, you don't play this game. This game is reserved for those who have charges only. And like the force of gravity that we learned, if you have a mass, you play the game. Force of gravity is between masses, regardless of whether or not you have charge, positive or negative, or no charge at all. You still have gravity, the force of gravity always there. However, the electrostatic force requires charge. When I rubbed this rod on my skin, what I did, actually, I was stripping it off of charges. In either case, I left it with a positive charge. What it did in here, this one was neutral. It did not have a charge to begin with. Let me remove the share screen to explain what happened. So basically, when I rubbed it, I put charges on it, really. I removed charges from it. So at the end, I left with a net positive charge in here. So what I ended up doing in this case is when I brought it near this piece of paper, the piece of paper is neutral. It does not have a charge. I did not rub it. I did not remove any of the electrons off of it or added electrons off of it to it. So what happened in this case? This rod induces, that's why it's a kind of a weak interaction. You saw it sometimes falling apart a little bit. It's not sticking 100%, because if it is positive in here, it will induce a negative charge in here and a positive charge on the other side, and now attracts it to it, okay? Similar to the balloon experiment. Let's see if I have a balloon in here. Do you guys have balloons in your homes? Try this at home, okay? It's a lot of fun. Let me see if I have a balloon in here. I think I do. But it may or may not work, okay? We do this in class. We do this in class a lot. but because of the shear weight and because of the humidity of the wall, it may not work. Let me remove the background again. Okay, let me focus it more on the wall in here. Okay. So I'm going to do the same thing. I'm going to actually charge this and try. It may not work, okay? I don't have much hair to do it. Otherwise, I would have probably, if you guys have a lot of hair, and I know some of you do, probably try it with your hair, okay? It works better with the, or if you have a cat or a rabbit, it works better, okay? So now it did not stick. Because it depends on the humidity of the wall also, okay? That plays a role in here. It can nullify this effect. So again, what happened if it worked, and I know it has, you have it in the, we do it in the class and it stays there for a few days actually. Or at least, yeah. A lot of fun when you play with that. Okay. Let me try it one more time. Of course, this shirt in here is really not the best. Honestly, it's the hair that works better. Hey, what do you know? It works, okay? So this is the electrostatic. What happened in here, I have it charged, okay? And it induced the charge inside the wall. Again, it provided, it put the charges toward it and repelled the opposite charges to the other side. And now they stuck with one another. Isn't this fun? Sounds good?
Yeah.
Okay, you guys are gonna try it at home, okay? And show us pictures. So that's the challenge of the day. Balloon. Sticking to the wall. I want you guys to share pictures, okay? And share your picture. Okay. Sounds good? Okay, so let's continue with the topic now. So we wanted to understand something like this. We really have to understand it in order to see what's going on in here. I'm gonna leave it there. Oh man, it's falling. Ed gave up. Let me move the chair out of the way. Ed gave up. Okay. Fell completely to the ground because this is an induced force, and the induced force is not strong enough. Actually, let me go back into the background again. Okay. So let me share the screen again so that we know what we're doing. Everybody understand what you're supposed to do with this first task?
Yeah.
Okay, very good. Thank you. Okay. So again, this force is proportional to the charges themselves. If you don't have a charge, this force is zero. If you have little charge, this force is little. If you have a lot of charge, this force is a lot. It's proportional to the charge, or the product of the two charges, and it's inversely proportional to the square of the distance, meaning the further away, the weaker the force, by a square law. Meaning if I double the distance, the force drops by 1/4, because 1/2 squared is 1/4. If I triple the distance, the force drops by 1/9, because 1/3 squared is 1/9. To quadruple the distance, let's say they were here, and now we make it 4 times, the force drops by 1/16. Because again, the square of 4 is 16, okay? So this is what observation has done. There is no proof for this one. I mean, this is based on observation. A lot of people worked on this thing, and Coulomb put it together. Hence the name Coulomb's law. That constant K there has to do with the medium where you do this. it has this number in here, 1 over 4 pi epsilon naught, where epsilon naught is called the permittivity of the medium. Okay, that's just a constant, just a number. Actually, to be more specific, that number is a big number. It's 9 times 10 to the power 9. It's a huge number because we want this one to be in force, and the force is in Newton, and the charge is in Coulomb, and this charge is in Coulomb. So you have Coulomb squared divided by meter squared, and we know the force is a kilogram meter per second squared. So we need this one to fix the units, number one, and number two, to fix also the definition of the Coulomb. That's why the number is big. But it's just a number, okay? It's a constant K. Depends on the medium. It's a property of the medium, really, how much it's allowing for these interactions to happen between it, okay? For vacuum, like I said, or even air, it's 9 times 10 to the power 9. For different media, it's a slightly different value, but ignore that for right now. Focus just on the product of the charges, proportional to the charge, and inversely proportional to this, the distance squared. That's the key. The main point is this force, the one I was demoing with the rod and with a piece of paper, or the one with the balloon, has this property. It's proportional to this, to the product of the charges, and the inversely proportional to the square of the distance. Okay. So again, when you read about it, one key thing is this charge. This charge has some fundamental properties. It's one of the secrets of nature. So what is a charge really? I answered that question by asking you, what is a mass really? So it's a property of an object, just like the mass is. There is no secret or myth or kind of, just a property, like any other property, okay? There is other fundamental properties we will see down the road, but this is a fundamental property. It turns out that it's always a multiple of this number, which is a very tiny number. It always comes in increments in full numbers. Either one of this, for an electron, it's 1.6 times 10 to the negative 19 coulombs. If you bring 2 electrons, it's going to be 3.2 times 10 to the negative 19 of them. If you bring 4 coulombs, it's going to be 4 coulombs, 4 electrons, I'm sorry, you're going to have 6.4 times 10 to the negative 19, and so on and so forth. It's always a discrete increments. It's always increasing in this chunks of this value. This is a property. So when we talk about electricity and it's a flowing, we think of a fluid of water, okay, flowing fluid. But in actuality, what's going on is it's coming in chunks, in bits, if you wish. Each and every one of them has this value. Don't get confused, though. This does not mean that it's actually chunky. Because if you open the faucet in your home, you think it's a flow of continuous matter, continuous water coming from the faucet. That is not true. You know, and I know, that the individual molecules that make up that water are H2O. So it's actually coming in H2O increments of H2O. So there is one H2O followed by another, followed by another, followed by another. So if I have a way for me to count them, I can tell you exactly that they're coming in chunks also. It looks to me like it's continuous flow. There is no distance between the first and the second, as if it's just one thing coming through. That is the same passion also for charges. They appear to be continuous because this number is so tiny. So this is the fundamental charge. It's a property of nature. It's one of the mysteries that we want to understand in fundamental science. Where did that number come from? Okay. regardless of where the electron is, or the proton for that matter, which is another problem. Why in the world the proton also has the same charge as the electron? Numerically, one of them is positive, the other one is negative. That's all. But number-wise, they're exactly the same thing. And one of them is big in terms of mass, and one of them is tiny in terms of mass. But when it comes to the charge, they're different. Now, charges, they always come in this multiple number, always. That is one property in nature. The other property in nature is charges are conserved, meaning whatever you start with in terms of charges, you end up with in terms of charges. This is a critical thing trying to understand circuits, trying to understand what's going on in here, or what's going on in here. Because at some point, like for example, between these 2 points in here, I have a branching, okay? Where is the pen or something I can show with it? Do I have anything to show with? Yeah, I have a toothpick in here to use for a demo. Somewhere. Here, those two, there is a branch in there. So that means the charges, they come in and they split. If you have, let's say, for example, for the sake of argument, 100 charges come in, 100 electrons come in. When they split, and let's say, for example, 60 of them went one way, 40 must have gone to the other side, because again, charge is conserved. This is one of the fundamental laws in nature. And you will see it helps us understand what's going on in here. Okay. It helps us understand what's going on in here. As a matter of fact, your house is full of that. If you look for it, everywhere you go and plug a device, it's 110 or 120 volts. I think it's 120 volts. 120 volts everywhere. Why? Because of this configuration. It's called a parallel circuit. Your house is in parallel circuits. You plug in all of the plugs, they're in parallel circuits. Okay? Unless you're doing a holiday decorations for Christmas, for example, where that light bulbs are one after the other, then it's a series, then it's this way. So a series is actually a special case. But most of the things that you have in your house is of this type. Okay? And that has to do with this law. The charges, when they come a branch, where they're going to split, they split in such a way that the incoming, whatever come in, is the same that is going to leave. Okay? You're not going to have a missing charge. One of them decides, you know what, you guys go, I'm going to stick around in here. No. There is no charge accumulation. In the same time, there is not a single charge that all of a sudden appears out of nowhere. Okay? All the charges that we start with and we end up with. Here is the deal though. How much charges do you have in a wire? That doesn't change. If you go, for example, to Home Depot today, and you want to buy conduit for the water, let's say, for example, there is a problem with the faucet or something, and you would want to change the conduit there. So you go and get the conduit, and they don't sell you the water with it. They just sell you the tube. The water is provided by the water company. So you remove the old one and you connect the new one and you turn the faucet and now the water company sends the water through it. So in this case, that's what you do. But if you go to Home Depot and you know what, I need also wire for my circuit somewhere in there that is gotten bad, I want to replace. What they do then, they sell you the water with the charges in it, with the electrons in it. Home Depot will sell you the wire with the charges inside of it. Now, when you say, okay, you remove the bad wire and you connect the new one, the power company does not provide you with the electrons. You have to bring your own electrons. What they provide you with is a force, if you wish. They provide you with energy to push those charges through the wire. That's all. If one electron moves out, they will replace it for you. So at the end, the charges will not change. At the end, the charges are conserved. Does this make sense to you guys? with the analogy with the water? Sounds good?
Yes.
Okay, very good. Okay, very good. So let me continue with the sharing of the screen. Okay, electricity, it's a lot of fun, but it's dangerous too, because these forces are tremendous. The force is tremendous, okay? What does a charge do? Here is the thing that we want to understand, okay? And this is critical because for the next chapter, trying to understand what's going on for the next chapter. A charge, let's say, for example, I have a test charge, 1 coulomb. 1 coulomb is a tremendous charge, by the way. Remember, 1 coulomb has this many of them. By the way, most of the times in the wire, there is a huge number. It's much, not just one electron. There is almost an Avogadro number of them, a huge number. Not probably an Avogadro number, but it's in that order of magnitude. It's a huge number, okay? You cannot even count them, but I'm saying hypothetically 100 and 200 just as an example, but you know that the number is much, much bigger. So let's say, for example, we bring so many of them that they give us 1 coulomb, which is a big force, by the way. Because if I have 1 coulomb and I have 1 coulomb and they're at a distance of 1 meter, so I have 1 times 1 divided by 1 squared, which is 1. But don't forget this number k, and I know I already told you about that number k. And let me go back into here to share with you another screen in here. Because we really have to have a sense of these things, what they mean, okay? Let me stop sharing and let me share another screen now. So let me bring in here. So what I said in here, I have Q1 is 1 coulomb. The symbol for coulomb is C. That's a charge. That's a lot of charge, by the way. It's a huge charge, okay? You don't run into it in the street, because if you do, that's a huge charge. You run usually into the microcoulomb or the nanocoulomb. That's actually manageable charge. But this one is actually tremendous charge. But just for the sake of argument, let's say we have 2 of them. And let's say I place 1 in here and 1 in here. It doesn't matter the signs. Let's put them, well, 1 is negative and 1 is positive. So now we know that they're going to attract one another. And let's put this distance between them exactly 1 meter. That's a big distance, by the way. 1 meter is this much, okay? It's a big distance, okay? It's a big distance. It's not a centimeter or something. So according to the expression, the force between them, they will be attracted to one another with this force, which is 9 times 10 to the power 9. This is K, the one I was telling you, which is 1 over 4 pi epsilon naught. When you plug in the numbers, that's how much it's going to be. Times 1 over 1 squared. And that is going to be 9 times 10 to the power 9 newtons. That's tremendous force. They will smash into one another with tremendous force. You cannot hold them together because 9 billion newtons is a lot of force. 9 billion newtons. That's tremendous force. That's what that force is. So it's a big, big force, okay? Your own weight, how much you weigh, is maybe about 700 or 600 Newton. So imagine yourself holding about what 10 million of you on your head with your hand. That's a lot. You cannot. It's too many people that you cannot. You cannot even probably carry 5 people at once. You have probably to be a world record holder or something to do that. I don't know what the world record is, but let alone this many. So tremendous force this one is, okay? It's a huge force. That's why we usually don't run into 1 coulomb in the street, I was saying. Maybe a microcoulomb, which is 10 to the negative 6 coulombs, or a nanocoulomb, which is 10 to the negative 9 coulombs, or something like that. All of the electronics that you see it, it's in the nano. Sometimes when it's big, it's in the micro. These guys, the capacitors, they hold charges. That's their role. They hold charges. Here is one for you guys. 1 drop. 1 drop. This is a device that is used specifically for holding charges. I'm looking for the value in here. And this is 22 microfarads. That means it can hold microcoulombs in it. Okay, it cannot hold the number in here that you see in here. That is the value in it. Mu is micro and F is farads. So this is a capacitor used to hold the charges. Usually you would want those in the circuits to prevent any kind of sudden charges or increases in charges, or you unplug the device so that there is at least a little bit for it. That's why they use them in electronics a lot. Anyway, so let me share with you the previous screen so that we know what we're doing. Share this screen. So one of the key things is that a charge of 1 coulomb will change its surrounding. A charge, 1 coulomb, or doesn't matter how much I have, will alter the environment around it. Will change the environment. It doesn't matter how much you bring, okay? Because here is how I find out. This is the idea behind it. Let's say I have a charge in it, I don't know, Q, it doesn't matter, okay? And if I bring 1 coulomb, this is my test charge, 1 coulomb, okay? And if I put it in here, it's going to be subject to this force that I was talking about. K times the 1 coulomb times that charge divided by the distance squared. If I bring it closer, the force will be stronger. Meaning if I take a spring attached to it, that spring will stretch so much, okay? So if I have this one and I attach my 1 coulomb, it's going to stretch so much, depending on how far I bring it from it. So this field will become stronger near the charge and weaker as I move away from the charge. This is how I represent this field. This is called the electric field. And it's a real thing. It's not an imaginary thing. The charge will change its surrounding, and it will change it with this thing. Okay, the electric field, okay? So let me go back into the notes in there, because these are some key ideas. I know that you're supposed to be doing the reading. You have the PowerPoints, which hopefully will help you understand some of this stuff, but also you need to do the reading. But just let me discuss this few points with you guys, if you don't mind. So I have a charge, Q, and I bring 1 coulomb. This is my test charge, okay? Imagine me carrying this charge with me all the time. Of course, this is not practical because 1 coulomb is too much charge. This charge will be repelled, assuming this is positive, of course, will be repelled by this force at this point. If I move it further away, this is how much it's going to pull on the string. This is the force basically it's going to pull. If I bring it closer, it's going to repel even more and more. You understand? So what I do in this case, I connect these lines in here, and I say this is the representation of the electric field. If I move it in this direction, I'm going to have a similar representation. This way, I'm going to have similar representation. This way, similar representation. If I come through this angle, it's a similar representation, and so on and so forth. These are the field lines. And this is called an electric field. Okay? This is an electric field. Because again, my test charge was just a test charge, a hypothetical test charge. But if I bring a real charge now, a real charge, okay? Not a test charge, another charge, Q prime, if you wish. That Q prime, and put it in here, it's going to be the field in this point times that Q prime. That is the force, the actual force I'm going to read on it. Obviously, if this charge is negative, the picture will be reversed, that's all. If this charge happened to be negative, not positive, the field will be pointing inward, that's all. That means if I bring a positive charge now, Q prime still, it's going to rain on this one. It's going to fall on it. Versus the first case, if I bring a positive charge and this is positive, it's going to be recede. It's going to recede away from it. It's going to move away from it. Unless I hold it with a spring, then I will see how much the spring is stretching. Okay. Same thing in here. It's going to rain unless I hold it with string. Then I'm going to see how much it's stretching. Now, if we bring this two together, a positive charge and a negative charge, and put them one to the next one, to the other one, the field will leave the positive and end in the negative. The field will leave the positive and end in the negative. The field will always leave like this one. In here, it's going to arc more, and in here, it's going to arc more. In here, it's going to arc and go around and come back in here. This one is going to leave, always leaves the positive and ends up in the negative. At this point, it's going to go from here, circumvent the entire universe and come back from here. Okay, so this is called actually an electric dipole. And it's a very, very important device because that's actually the antenna. Okay, actually a very, very important device. The other device that you have it actually in the notes, and the book talks about them, and hopefully you understand it, is the parallel plates. The parallel plates is on one side, I have a positive charge. On the other side, I have a negative charge. So what the parallel plates do is the electric field will always be parallel and coming in this direction. I'm neglecting the edge effects, ignoring the edges. Because in the edges, actually what's going on, the field starts to bend. This device is what I have shown you earlier, actually. It's in the book. This is actually called a capacitor. Okay, this device is actually a capacitor. The usefulness of capacitors is to trap the electric field. Because the electric field would be mainly in this region. As a matter of fact, if the plates are too big, the electric field will be zero here, and the electric field will be zero here, and all of the electric field will be trapped inside the plates. It's actually a good device to have around, capacitors, because you could actually trap an electric field in it and walk around with it. As a matter of fact, I have a camera on my car. I placed it before I traveled not too long ago that has capacitors to charge basically the camera when you put it in the parking mode, because it doesn't have battery, the camera, it has capacitors. So if something happens to the car while it's parked, it pulls energy from the capacitor and basically records the event, if in case somebody hits your car while it's parked, and saves the incident on the memory chip. The point being in here is that that is a capacitor instead of a battery, because it's the same thing. You're storing energy. Okay, so let me go back into the points in here and make sure that we cover all the stuff we're supposed to cover in here. Let me stop sharing. Let me share with you guys. So again, I mentioned the energy. There is an intrinsic relationship between the electric field, between the energy and the electric potential. The potential is the one I mentioned, 120 volts. So what the power company does for you is it provides you with the potential. Every plug in your household should have the same potential, unless you have a dryer or one of those big devices that require much more voltage. But the voltage is exactly what the potential is. Now, that potential doesn't do anything. If it is just sitting in there, the minute the light turns on or you plug a device to start charging, then it drains energy. The potential doesn't change, it's always the same. But how much charge you drain from it is exactly the energy. That is what the power company will bill you for. It tells you how many kilowatt hours you have consumed, because a watt is actually a power. A watt is a power. Or a kilowatt is kilopowers, basically that many power. for every hour, that becomes energy. So that's how, and that's what really matters. When we study physics or study chemistry or do engineering, or nothing really matters until we do an energy, until we account for the energy. Because that is really what we pay for, is the energy. And that is really what we get paid for, is the energy. The energy is a currency, really, in all of this. And that is actually currency even in everywhere, okay? Even in the power. So when the power company sends you a bill at the end of the month, what they're billing you for is how much energy you have consumed. They don't bill you for the fact that they have 120 volts in your house. I mean, they may have memberships on or taxes and whatever those nonsense stuff that they put them in their service connections and all of these things. But those are fees. The actual bill of how much you have used, it depends on how, if you, in other words, if you turn off all of the lights and plug all of the devices from your household, the only thing you should pay for in this case is the connection fee and whatever state and regulations basically you have to pay, but you're not paying for energy whatsoever. Okay. So this is the idea behind it. So let me go back into that screen where I was earlier to understand some key relationships, because we're going to be using them. So we said the force is equal to QE. The force is in Newton. So this is a Newton, the unit for the force. The unit for the charge is Coulomb. Obviously, the units for the electric field need to be in Newton per Coulomb. So that's a natural unit based on this relationship. There is another relationship that people use, and I'm going to define it very quickly. It has to do with the voltage, because the electric field times the distance is related to the voltage, okay? And I will explain what the voltage is in this case, okay? If I go back to the parallel plates, and I have an electric field in here, and I calculate the voltage between these two sides in here, I will find that this is the relationship between them. So the unit actually that you will see probably used extensively in the book is volt over meter. So this is the unit for electric field. And what is that volt? It has to do with the energy at the end. The energy usually when we are doing an electricity, we use the symbol U for it, is equal to the charge Q times the voltage. So this is the potential. This is in volt in honor of Mr. Volta, who did a lot of work, among other things, to invent the battery. Okay. The volt, remember this one is Coulomb. This is in honor of Mr. Coulomb, who put all of these things together. In the system of units, the Coulomb is not a fundamental unit. Remember, the fundamental units are M for meters, K for kilogram, S for second, and A for ampere for the current. Okay, so you have M for meter, K for kilogram for the mass, S for second, and A for ampere. It turns out the ampere and the Coulomb are related to one another, because a Coulomb over a second is actually an ampere. So the Coulomb is not a fundamental unit, but it's equal to a fundamental unit. This is A, which is a fundamental unit, and S, which is a fundamental unit. Both of them are fundamental units. The Coulomb is not. The Coulomb is a derived unit. Just as the Newton is not a fundamental unit. The Newton actually is equal to mass times acceleration. Mass is in kilogram, the acceleration in meter per second per second. Again, that is the Newton. So the Newton is not really a fundamental unit. Again, the energy is actually in joules. And the units for the energy are in joules is equal to the Coulomb times the volt. So this is what this expression is saying. The energy is in joules, the Q in Coulomb, and V for volts. So this is just a refresher on the units, and sometimes it's a useful refresher. The joule is a force times distance. Work is a force times distance. So this is actually a kilogram meter per second. That's what the Newton is times distance. So it's a kilogram meter squared per second squared. That's what a joule is. So I can break down everything into the fundamental units. This one I just said it's an ampere times second, and this is the volt. Now I can say what the volt is, which is not a fundamental unit. Also, it's a derived unit, and it's nothing but a kilogram times ampere. I'm sorry, times meter squared divided by an ampere second cubed. So again, I can express everything in terms of fundamental units. All the 4 units that you need to remember, I am KSA, okay? But the point being in here, this is the volt. So that's how much the power company does for us. So the power company will provide 120 volt, okay? That's how much it is. This battery is 1.5 volt, okay? So this is how much bad energy it can do. I mean, how much potential energy it has. So if I drain 1 Coulomb off of it, I drained 1.5 joules off of it. If I drain 2 coulombs off of it, I drained 1.5 times 2, which is 3 joules off of it. Obviously, if I buy this one and I bought it and I use it and I drain any charges from it over a while, over a long time, it's not going to be able to provide any more charges. So it becomes useless. I have to go and buy another one. Okay, so this is a D battery, and you have the AAA batteries and the AA batteries and all of those different rankings of the battery, the battery size and how much actually charge they can deliver. But at the end, they have the voltage, which we can use in here. I have a battery holder in here. This is for the AAA. The point being in here is this is basically the idea behind all of these things. Let me stop sharing the screen in here and share with you another screen to continue these points. Okay, again, the current I defined it to be the charge over the by unit time. Basically, how many charges flow per unit time? That is what the current is. So when I wrote the current A to be equal to Coulomb over second, that is exactly what that expression is coming from. It's the rate at which charges are going or increasing or decreasing. Okay, let me write this definition because it's a beautiful definition that we really need to remember, because somebody might ask you this question. Let's say, for example, you're walking in the streets and somebody comes to you, hey, can you tell me what the current is? So you should be able to tell him what the current is. So the current, this is the second item of the discussion, by the way. The current is the rate of change of charges. Okay, let's say, for example, I have a conductor in here. This is a conductor. Okay, and I have charges in here. If these charges are not changing in time, then I don't have a problem. There is no current. But if these charges are moving in one way or the other, so in this case, they're changing with time. So in this case, the current I is the rate at which the charge Q is changing with time. So I really have to wait to see if there is a change. It's like the velocity, if you wish, which is distance over time. This is actually charge over time. That's why when I wrote it earlier and I said that this is in ampere and this is in a Coulomb and this is per second. So in this case, the Coulomb was an ampere times second. That's how I wrote it earlier. So that is what the current is. So if somebody walks to you on the street and tells you, hey, what is the current? You should be able to tell them it's the rate at which charges are changing. The rate in time, of course. Make sense? So this is the second item.
Yes.
Sounds good? Okay, very good. So let me stop sharing the screen in here. Well, let's see how we're doing on time. Still have time. Which brings me, this is again not in lieu of your reading. Again, I'm just warning you guys. So you may have a different perspective from me and different view, but hopefully you guys can go into the reading, because we're going to do an example from the book today, problem 52. Okay. Ohm's law relates the voltage to the current. Ohm's law says the voltage is proportional to the current, where each material has its own property called the resistance. Okay, so again, let me share with you the other screen so that I can write it down. So Ohm's law says basically the voltage, remember this is the voltage, this is the potential, is proportional to the current, and the constant of proportion. So this is the current, and the constant of proportionality is the resistance. The resistance depends on the length of the wire. The longer it is, the more resistance it will have. It depends on the cross section. The wider it is, the less resistance it's going to have. And depends on the material. Some materials are more resistant than others. Okay. Wood has high resistance. And so is air, by the way. Otherwise, if the air is not a good resistor, we will have a problem because of the fact that there is charges on the wire, so they could fly and jump on us and basically cause all kinds of problems. So those are two examples. On the other hand, copper or silver, and copper, yes, and all metals actually, and iron to some extent are good conductors. That means they have low resistance. So these are called actually conductors, and these are called insulators. Okay, and the law that governs them is Ohm's law. Again, Ohm's law, V equals to Ri. Okay, sometimes Ohm's law doesn't work. In the case, for example, of transistor, or in the case of a diode. Okay, and those are called the non-ohmic circuits or non-linear circuits. The reason why this is linear is because modern electronics does not, I mean, it has parts in big time linear that obey Ohm's law, okay, especially near the power supply and everything else, but there are other parts that you can basically simulate Ohm's law for them, okay, which is important law, actually. It's really important, even for modern electronics, it really still governs these things, what's going on in that. Which brings me to the last point of the circuits in here, and the last point of the topic, which is the circuits. You can take two components. Let's say, for example, resistors. This is the symbol for the resistor, by the way. This is the symbol for resistor. So when you see this, what they're talking about is this device that I was showing you earlier. It's this tiny things in here near my this things in here. Okay, those are resistors. Let's say, for example, for the sake of argument, I brought 4 ohms. I know the book gives you different numbers. Let's throw in different numbers just for the sake of argument. And let's say, for example, in here I have 8 ohms. Okay, obviously this, as if, not really, as if I have only one resistor in here. So this is called a series. And this resistor is 4 plus 8, which is 12 ohms. Okay, I could have done this way. So what happened in here, the charges I was talking about, they come in here, they go through this 4 ohm, and then they emerge off of it. Conservation of charge, the entire charges will come through it. And then all of a sudden, in this case, they'll go through this one in here and they emerge from it. So the current is the same. Same. So this is what means to be series, current, the same. And in this case, it's the same charges that came through the whole thing. This is not really, this is as if, this is called equivalent. Okay? Let me show you another configuration. Let me have a breakpoint in here and split this two. So I still have the 4 ohm on one side. I know in the book you have a different example, but that's the same thing. It's the better. And I have 8 ohms in here. Okay. This is as if, not really, as if. So here is the problem with this circuit in here. I have charges in here that come in here and emerge off of this. But some of them will choose to go through the 4 ohm. Actually, a lot of them will go through the 4 ohm because it has the path of less resistance. And this has a high resistance, so some of them will go through this one still. They split in such a way, they emerge off of this, the splits, the portions, and then when they merge, they measure back exactly of how they started from. Let's say for the sake of argument, I have 12 charges in here that came in. 8 of them will go here, and 4 of them will go here. And at the end, 4 of them will emerge from this, and 8 of them. So they combine back to 12 charges again. And I wrote it in this person, presented this number just in purpose, okay? So that in this case, the product of the charge times this number times the resistance is the same as the product of this one. So that's how they split actually. Because the voltage is the same. So this is called a parallel. And this is mainly what you have at home. So this is a parallel. So in this case, the circuit will split in such a way the voltage is the same. Not the current. As you can clearly see, the current is not the same. There is more current in this way, or more charges on this way than charges on this side. But the voltage is the same. The product of these two numbers are the same. In other words, the current here is the same and the voltage is the same. This is as if, not really, as if. I have the following. I have 12 charges, came through an equivalent resistor and emerged off of it 12, okay? This resistance, I'm going to find it by taking the inverse of 4 plus the inverse of 8 and invert the whole thing. So basically 1/4 plus 1/8, which is what? 3/8. So the answer is going to be 8/3. Let me do the calculation correctly so that I'm not giving you some wrong number in here. So basically what I have in here, what is my calculator? Is it open? Oh man, I don't have my calculator ready. Mathematics. Let's do that. I don't want to give you the wrong numbers in here because. Okay, so what I have in here, I have 1/4 plus 1/8, the whole thing inverted. Yeah, 2.666 something, 2.66, which is 8/3, as I said before, 8/3, which is 2.67 ohms. This is a key thing to remember. This is a very important thing to remember. When I put them in series, I started with 4 and I had an 8. What I ended up with is more than the biggest of them all. I ended up with 12, and 12 is more than 8. When I started with 4 and 8 in parallel, I ended up with an equivalent less than the smallest of them all. The smallest in this case is 4. And the number, the equivalent, is less than even that. So this is the equivalent again. This is not really, this is the equivalent. On that note, I'm going to open the book. And hopefully, you will have homework, by the way, from this chapter. You're not going to have a quiz on it, okay? So you're going to have homework on it, assignments, okay? So I'm going to have problem 52. Am I still sharing my notes or not? Because I don't know where I'm at right now.
Yes.
I can stop sharing. Okay, very good. Thank you. So we're looking at problem 52 from page 215. Okay. So let me look at this problem. First of all, the problem has this look in here in it. So it has a resistor. It has, I'm going to do my best to try it. Okay, there's another resistor, and it has a third resistor in here. No, the whole thing is a mess the way I do it. Okay. I should have at least the whole thing in the different. Okay, so here is the deal. So we have a resistor. If you look at it, it's like a triangle, really. I have another resistor in here. And finally, I have another resistor in here. And they are all supposed to be the same resistance. This is 6 ohm. This is 6 ohm. This is 6 ohm. Again, ohm is the unit for resistance, and it's not a fundamental unit, but it's actually a derived unit. And again, the fundamental units are MKSA. Okay. What they say in here is that a voltage of 12 volts is impressed across one of the resistors. Since they are the same value, it doesn't matter where you're going to put it. I'm going to put it in here, okay? So there is a 12 volt in here. In other words, 12 volt battery, which is the car battery that you have in your house, okay, in your car. So that's actually 12 volt. So there is a 12 volt battery in here. Think of it. That was put in here, okay? The question is, how much current is in that resistor? So again, the current will leave this battery, will split in here. Some of it will go through this one, and some of it will go through the other one. The question is how much this current is through this battery, okay? So that's a question that we have to do. First, I need to know what this value is, the overall current, okay? Once I know that, I know how much went to each one of them. So this is really a multi-step problem, and it's in your book, so you really need to understand what's going on. So let me redraw this shape in here. It looks kind of, these are in series actually. This is one after the other. As you can clearly see, this 6 ohm, which I'm gonna label 1, and this 6 ohm, which I am gonna label 2, are actually in series. So what I have in here, I have 12 ohms between this node, this is called the node, by the way, and this node. I have 12 ohms on this side, but I also have 6 ohms on this side. But this is split now. This is actually, so this is how the circuit looks like now. It looks like I have a 6 ohms from the bottom. And the other part in here has 12 ohms in it. That's how it looks like, basically. When I analyze this, there is a 12 volts still in here. This is 12 ohms, and this is 6 ohms. So how much current will split on this one and the other one? Before I do that, I want to understand the equivalent now. The equivalent, remember, it's 1/6 plus 1/12. The whole thing is inverted. If I do that, according to this calculator, there's going to be 1/6 plus 1/12. The whole thing is inverted. And this is going to be 4 ohms. This whole thing looks like this. 12 volts across a 4 ohm. So basically, I resolved everything to just one resistor. Okay, that's it. So what happened in this situation is I went from the actual circuit, combined these two that are in series into one, which is 12, and then combine this two now into just one, which is this one. Remember, 4 is less than the smallest of them all, which is 6. It's always true. When you do things in parallel, the number for the equivalent is always smaller than the smallest. When you do them in series, because both of them are the same, it's going to be bigger than the biggest. 12 is bigger than either 6 you like to pick. Okay. So in this case, how much current is flowing? We apply Ohm's law. We apply Ohm's law. Ohm's law says V equals to Ri. R is 4. V is 12. So that means I is equal to 12/4. And this is 3 amperes. So this is the overall current. This is 3 amperes, 3 amps. Part of this 3 amps went this way, and the other part went through the other side, okay? I can find this current now to test it, okay? I needed this step for another purpose, okay? Let's find this current now. This current, I have 12 volts and I have 6 ohms. I can find this current by doing Ohm's law also. I have 12 volts equals to 6 ohms times the current in here, which I don't know. I'm gonna call it I through the 6, okay? Through this I current. So obviously it's going to be 12 volts over 6 ohms. So this current must be 2 amps, I'm sorry. So 2 amps is here. 3 amps come in, 2 amps go this way. So how many amps must go through here? It's clearly 3 minus 2, which is 1 amp. Another way of finding it is actually going back to the same argument that I made earlier. The current that is flowing, the voltage is the same. That is part of the parallel. So you have 12 volts and 12 ohms. Again, you apply Ohm's law for this portion. It's going to be 12 volts is equal to 12 ohms times the current I. I then is going to be 12 over 12, which is 1 amp. So indeed, this is 1 amp. This is 3 amp, and this is 2 amp, and the overall current is actually 3 amp. You see here, my argument earlier that the charges do not get destroyed. When they come in here, they split themselves. 2 amp go one way, 1 amp go the other way, and then when they recombine, they're going to be 3 amps again. I know I went the long way to do this problem. We could have done it much quicker actually here, using this argument, 12 over 6, that's 2 amp. 12 over 12, that is 1 amp. So it's 1 amp in here and 2 amps in here. Then I would infer that 3 amp must have come in from the battery. But I needed to check that. I needed to make sure that indeed 3 amps came from the battery. For me to check that, I do this analysis in here. I combine these 2 lines together to make them 12, and I combine this to make them 4. And now 12 over 4 is indeed 3 amps. So it checks. So there are 2 ways for me doing this one, either the long way or the quick way. And at the end, I should find the same answer. If one gives me a different number than the other, then I have a problem before me that I really need to understand where the issue is. Okay, I promise the problems that I'm going to assign are not going to be that hard. Okay, but you really need to work with together from this chapter. So we're done with this chapter. We're done with this concept. Okay. Again, watch for the assignment from next week that is going to be referring to this week, in terms of homework, because this requires some hands to get dirty. In other words, some calculations, okay? And to get them going, okay? Sounds good? So we have 2 items of discussion. The first one is the definition of the current. Okay, you go to the store, for example, I don't know, you go to Walmart and the person who is in the front asks you, hey, what's the current? You should be able to answer it. Okay. It's the rate at which the charge changes with time. Okay. And then the other thing is, I'm hoping that you guys will do the balloon. Okay, if you cannot do the balloon for some reason, try to do the if you have long hair, try to, instead of using a rod, you can use actually a comb, okay? Yeah, okay, rub it very well, and you can do the demo and demonstrate the electrostatic force. Sounds good? Don't forget you have 2 quizzes, as Sabine mentioned earlier. Due on the same day next week, of course, they're not due. They're due this weekend. The 9th is when? Oh, it's this weekend, this coming weekend. So they are due soon. One from the week before last week and one from the last week. Sounds good?
Yes.
Okay. If you guys don't have any question, I'm going to stop the recording. And I will see you guys next time.